and then there's something called absolute convergence for these two. So first of all, the term alternating, the alternating term is -1 raised to the n. And the reason why this is the alternating term is because that as n progresses, you are getting the sequence. So if n is equal to 1, you have -1, then 1, then -1, then 1, -1, 1, and then dot, dot, dot. So this would be the alternating sequence. And what you can do is you can add the series, make it into a series this way, starting from 1 going to infinity. And then you can argue whether this, well, check mathematically, not really argue, it's not philosophy course. You mathematically check using definitions, theorems, and so on, if this is, well, theorems, if this is convergent or divergent. Now, see, what is your intuition? What does your intuition tells you? What is the, do you think that this is divergent or convergent? Remember, we are adding infinite strings of -1s and positive 1s. So what does the intuition say in this case? Yes? Now, no, this is always equally distant because it's -1, it's always on the -1 level, +1 is always on the +1 level. And you are trying to add them all. So technically, this is -1 + 1 - 1 + 1 - 1 + 1 - 1 + 1, and it goes like that forever. So what is your intuition about it? Would this converge or diverge? So I already have the 2 students claiming that this should converge at 0 because you would like to cancel all these ones, right? Cancel the first 2, cancel the second 2 pair, right? Second pair, third pair. If they're all paired, right? So that's what our intuition tells us. But unfortunately, no. Right? So we'll have to take a look at what happens here. But first, let's take a look at the theorem for alternating series. Obviously, the sheet that I gave you has the definition. And if you actually looked at the definition on the sheet, right, and you looked at the thing, you would know immediately what's happening, but you didn't look, right? You wanted to reason, and I told you to retire the reason and the common sense and just learn the sheet instead. So it does not converge, this one. No. Because if you take a look at the positive, you see that the condition for convergence is that the next term, an plus 1, must be smaller than an, which means that the only way this converges is if you have a decreasing sequence. Right? And what is the sequence of 1, 1, 1, 1, 1, 1? Right? And not decreasing. So this one diverges. But we'll get there, right? This one diverges, but we'll get there. That guy is just peeking into the lecture. It's creepy. It's like overlooking what I'm writing. The people online are confused of what's happening, but it's awesome in the classroom. Anyway. So let's talk about the convergence and divergence and all of that stuff. So alternating series converges. Alternating series converges if 2 conditions are satisfied, and that is that the sequence AK is decreasing, and then the limit is equal to 0. So those are the 2 conditions that you must check. If both of those are satisfied, then it converges. And then that is going to branch into 2 different types of convergence. It's going to be a conditional convergence and then absolute convergence. So we are going to have, let me first write this, this theorem. So the alternating series -1 to the n, alternating series -1 to the n of an, where it goes from 1 to infinity. Now you can have n plus 1, you can have n minus 1, whatever. It's the exponent, it doesn't really matter. Converges if, number 1, an, well, let me just put the full, so 0 less than an plus 1 less or equal than an, and 2, limit of an as n goes to infinity is 0. So these are the two conditions, and then it will converge. So let's draw a diagram. So here is what this is also the procedure and a diagram of how you should think and which path you should take. So you are starting with a series of -1 to the n of an, from 1 to infinity, 0 to infinity, it doesn't matter. So you have this. And now what you do is you take and you look at the conditions, and then you will branch off into the convergence branch or the divergence branch. Now this is where you are checking conditions that an is decreasing and the limit as n goes to infinity of an is 0. So as you can see, if these two conditions hold, you have convergence. If they don't hold, you have divergence. That's the first branch. And then the convergence is going to branch further into absolute convergence and conditional convergence, where the test is that now you need the series of an to converge and series of an to diverge. Absolute convergence and conditional convergence. So absolute and conditional convergence. The summation of an, so the series an converges, or the series of an diverges. So observe that we don't use this alternating -1 to n ever in any of the. We know this is alternating series because in the original problem it's there, right? But then we only look at the an, which is the stuff that comes after this -1 to the n. So we don't have to worry about that -1 to the n. On the side note here, maybe I should do this also in red, but I'm just going to say note. Cosine n pi do you guys have anything to say about cosine n pi? Cosine n pi is the fancy way to write -1 to the n plus 1. It's the fancy way to write that. Because when n is equal to 1, you have cosine of pi. How much is cosine of pi? -1. So cosine of pi is -1. Oh, that should be just 1 to the n. And then how much is cosine of 2 pi? So when n is equal to 2, they both give you 1. So just be mindful of the cosine n pi. If you see cosine n pi in your series, you can replace it with -1 to the n, and it's alternating series. Those guys lurk around. They sneak in. So you have to be careful about that one. All right? It's a fair warning. I'm going to put it on every test. All right. So let's take a look at probably the easiest case we can have here, which is the alternating harmonic series. See? It's a negative 1 to the n over n. So just because you have negative 1 to the n, that means that you guys actually have the alternating series. Now, it is important for you to be able to deconstruct this. You know that you have negative 1 to the n piece, which you're not going to use for anything. And then what's a to the n equal to? It's equal to 1 over n. Are we all clear on that? When you put those two together, you get your series. Very good. A to the n is anything besides negative 1 to the n, or if you have cosine n pi. Perfect. So now, what do we do? Well, remember, we are starting with our series. And I'm going to do this as a tree first, and then we can break off from it. So now, this could either converge or diverge. We have to check our conditions. The condition says, is an equals 1 over n decreasing? Yes. Good. Number 2, is limit as n goes to infinity of 1 over n equal to 0? And here I am with the blue, checking off both of these conditions, which means that we already earned convergence. We all know that the series of 1 over n diverges is a harmonic series because of the p series or integral test. Pick your poison, right? But here we see that the alternating harmonic series is already on the convergent path. You see, so these small adjustments here and there, they make a big deal. Now we are supposed to figure out whether we are talking about the conditional convergence or absolute convergence. Now remember, for that one, you have to check the summation of 1 over n, which is the series of an. Now, is this convergent or divergent? Series of 1 over n? We just talked about it. It's a harmonic series. It diverges by p series. I'm going to give you a tip of your lifetime. So, conditional convergence, that's the answer. So we say that series negative 1 to the n over n, conditional convergence by alternating series test. Done.
So, can you explain that real quick? If you go up just a little bit, right there. So series converges and then diverges, which means that that's where it's converging.
Yeah, this is the, well, I'm going to explain that concept. I'm going to explain that concept because, you see, why is it called conditional convergence? Under what condition? We know, I'm going to put it in here in red, we know that summation 1 over n diverges by p series, let's say. Also integral test. And this is used so much that you might as well want to memorize this one forever. All right? Imagine you're 20 years, you're at some party somewhere, and pops up. You want to know that one. You want to be cranking that, remembering p series test. Just memorize it. Do yourself a favor. So we know that series of 1 over n diverges by p series or integral test. If I replace that 1 with negative 1 to the n, and I make that alternating, it converges. And we say it converges conditionally. So it converges under the condition that alternating is there. If there is no alternating term present, it's divergent. If the alternating term is present, it's convergent. So conditional convergence. the absolute convergence, you will see it passes the tests, and it also passes the convergence on sum of an, which means that alternating term is not what makes it convergent. It's the presence of alternating term, -1 to the n, that makes this series converge now. So that's why it's conditionally convergent, because that term was there. If the -1 to the n is not present at all, you just have harmonic series which diverges. If you put in the alternation in it, the -1 to the n, it becomes convergent, and we drill a little bit deeper to say it's conditionally convergent, because if there was no alternating term there, it would diverge. Does this make any sense? And now the next problem we are going to do, we are going to try and focus on absolute convergence to see that everything converges down the line as we go through the problem and so on. Now, as we were going through this, and I heard that very scary thing which says that harmonic series is convergent to 0. So it's not that it's just convergence was wrong, but it's also said to 0. Limit of 1 over n goes to 0. Limit of 1 over n goes to 0. Series of 1 over n is the harmonic series which diverges, and then you do either p series or you do integral test. Now, what you could do with this sheet, once you've filled all of the extra stuff that I talked about, you can go and you can copy it on a smaller size and maybe put front and back, right? So you copy 2 on the same page, copy the length, and put front and back. You laminate that one. So you have a hat on the side like that, right? And you take it everywhere with you. Maybe you'll drill a little hole, put a little string around the neck. You can tuck it in, right? It will, since it's laminated, it will not get wet as you shower. Protected. You can have it with you at all times. If you know this sheet verbatim for every test, you're going to do amazing. If you use common sense, nothing against your common sense, but it doesn't work. You saw that. You made so many mistakes, and I did too. I did terrible in this section because I tried to use common sense. Retire it for this section. Please, retire it completely. All you do is memorize this. It says 1 over n. That's 1 over n to the first power. That's the p series. So there we go. I memorized that if p is 1 or more, if 1 or less, it's divergent. If it's more than 1, it's convergent. So because it's 1, it's divergent. So harmonic series diverges by p series. Unless you want to crank out the integral. Memorize this. It's literally, you're sitting down, repeating it 5,000 times, writing it down on the paper 5,000 times, and just apply these as they come about. All the secret to this section. Knowing the tests, figuring out which algebra fits where, and then using that algebra when it's needed to transform this and use it. Yes? Only ratio test at one point. Chapter 9 is something different, and we'll see what it is tonight, and it's absolutely awesome. Chapter 9 did not make much sense when I was doing it the first time, but immediately with differential equations when it kicked in. And usually you realize what calculus is and how these things work as soon as you're done with the class, right? If you were to open the book about 2 weeks after the final exam, you'd be amazed of how much stuff makes sense. And you would ask yourself, well, why didn't it make so much sense when I was actually taking it? And the answer is because you are way too much focused on the grade, and you are way too much stressed, and you are, under this pressure to succeed, so you miss. That's the reason. When you are calm and you open it because you're interested in it, it becomes very, very simple. Very simple. So you'll see that. Let's take a look at another problem. This is going to be summation 1 to infinity of n, negative 1 to the n over n squared. That's the series. Clearly is alternating series because of the negative 1 to the n. I know that an is 1 over n squared. Fair? So now let's crank our problem. So we start with, I have a series, it's alternating series, and I have to check conditions. The first one is, do we have, because an is equal to 1 over n squared, is it decreasing? Yes, it's decreasing, right? The graph would be like this. So it's decreasing. Good. And is the limit equal to 0? Is it? Yes. So we have both conditions fulfilled, which means that we have convergence for this one. The next step is to figure out what's happening with summation of an. Observe that I'm not using alternating part here. I'm just using summation. So guys, in the first stage, you only looked at the sequence an. You checked if the sequence an is decreasing, and you checked if the limit of the sequence an is 0. That's what you did on the stage 1 to check for overall convergence. Then you are going to take a look at the summation of an, which is the entire series without the alternating test. So that's going to be 1 over n squared, and now that one does what? Summation 1 over n squared. I'm just going to keep my poker face until you tell me either diverges or converges by the so-and-so test. Aha, converges by p series. Thank you. And I just ignored everyone else. That's it. Unless you tell me which test, and you have to tell me the reason, right? You all remember those times when you were little kids and you asked for something and parents or guardians or grandparents or whoever just said no. And you say why, and then there is just under discussion. Did you hate that? Right? So don't be like that. All right? Is it convergent or divergent? It's convergent because blah. Or it's divergence because there is no, I mean, it is 50-50 at the end, right? It's like one or the other. Flip the coin, see what happens. So it is convergent by p series. Now stare at the sheet, look at the p series. You clearly see it's 1 over n to the power of 1, 2, 3, 4, whatever. So if you have that thing, it's p series, so convergent because you memorize the conditions. So we know it's convergent. So there you go, absolute convergence. Absolute convergence. So now, why is this absolute convergent and how is it different than conditional convergence? Well, guys, look at the original problem. I'm just going to try to fit everything in. Look at the original problem. The problem here, original problem with the alternating series test, is already setting us on the path of convergence. And then when you take off the alternating part, we just get 1 over n squared. And it's still convergent. So why is the absolute convergent? Because it doesn't matter whether that alternating part is in or out. It converges anyway. Where the previous example, if the alternating part is in, it converges. If the alternating part is out, it diverges. Right? So that's the difference between problems that are conditionally convergent and absolutely convergent. Conditional convergence is under condition that the series has alternating term in. If you remove alternating term in, the problem will diverge, and that's it. So the other way is we are claiming that if you have the for absolute convergence, right, it doesn't matter whether there is an alternating term in or not, because the problem would converge anyway. So that's the difference between the two. Yes?
Just like a random question. Which one do you think is the hardest to notice and to have these tests?
10? Well, I don't think there is. See, when you are proficient in learning how the problems look like, the trickiest ones should be the comparison tests. They usually show, prove to be a little bit of issue. But then, what I find that the students don't do well is the integral test. Not because you have to integrate, but because you actually have to prove those three conditions and you get stuck there. Or you use the integral test when you are not supposed to use integral test because you never checked and proved the conditions. So sometimes you will get something that looks like, the simple U sub will solve this, right? So let me just make this into integral test and do it. But then one of the three conditions in order for you to do integral test doesn't hold, which means you can't use integral test. Tough luck, right? So what I found is, another thing, what I found is that students refuse to sit and study this thing, the sheet, to memorize the theorems. And then you use intuition, and we all saw what happens when we use intuition. We get wrong answers. Another thing is students refusing to test the divergence immediately to any problem. Sure, divergence is not going to work now, because if you set stuff to infinity, you'll get a number over infinity, which is 0. So we don't know whether it converges or diverges because it's a non-zero answer. But when it works, it saves you time. Last time we did that problem, if you remember, with factorials and exponential functions. We know in limit that it was supposed to diverge right off the bat. We still pushed and did the ratio test because we wanted to check the ratio test, sure. But, you should be resistant to actually doing this thing. Remember when we had the chapter 7 and we had integration, and it was all about which method we are going to use, and you try to do a method that you think it works. And then on the test, what happened? Problem number 2 was a U sub. I put the smiley face there. And we have, I believe, 3 or 4 students pushing and grinding through the trig sub, getting it right at the end, which is awesome, right? Getting it right. But it's a page and a half of calculations, right? Where you do the U sub, and you're done in 3 steps, right? So there was another instance on the test where with that, I believe, problem number 4, which is the problem that was the most ridiculous problem on the test. So problem number 4 was the one that, because you must have something that differentiates that A-level kind of student, and that would be problem 4, which looked like it's a partial fraction decomposition, but then if you studied hard enough and you knew that you can do partial fraction decomposition if you have multiple denominators, not just one, right? And I see that some of you actually went through partial fraction decomposition, but you didn't realize that you just went the full circle. Because when you calculated A, B, and C, you got 2 of them to be 0 and 1 to be whatever the number was on top. So technically, you didn't achieve anything. And that should say, well, okay, that's not the right method. Try something else, and the only other thing that you could do was a trig sub there, which is what some of you did and got it correctly, which is still awesome. So going back to our lecture at hand with the alternating series test and the use of the sheet and what you guys, the way you should approach this. If the problem is in geometric series form, which means you have some kind of exponential, 2 to the n, 1/2 to the n, you will immediately recognize that geometric series are your exponential stuff. E to the x, 2 to the x, 3 to the x, except now x is n. So if you have exponential function, whether it's 1/2 or 2 or whatever, that has to be geometric series. Then you say, okay, if I am able to do partial fraction decomposition or if I have subtraction, it's telescoping series. And those are the only two that can give us the sum. All of this happens obviously after you check the divergence and make sure that's not knocking off the problem right off the bat. Pretty much everything else should look unique in some way. P-series, well, you have a polynomial-looking structure. Remember, see, the n is the variable, which is in the base, and then the exponent is fixed. So you're going to have 1 over n cubed, 1 over n to the 7th, 1 over n. So in this case, right, that's the denominator is polynomial form, which is completely opposite from the exponential form, which means it's P-series. Obviously, for alternating series, you're going to spot -1 to the n being present at our problem. And then you're going to have, what else? Alternating series, you see the -1 to the n, or the cosine n pi. The root test, last time for the root test, we said that you guys are going to have this, the whole thing, the whole sequence raised to n, or raised to 2n, or raised to n squared, right? So root test is going to happen when you have something like that, and then you are able to cancel at least one of those n with the square root and nth root, and then you can do the limit and other things. Ratio test is mixtures. So if you have a mixture that looks like part of the problem is geometric series and part of this P series and there is a factorial and so on, as soon as you get all of these mixtures in, has to be ratio test. So it's very unique of how these things are done. And then obviously the comparison tests are spin-offs, usually spin-offs of they're spin-offs of P-series and so on. So you just figure out whether direct is better or the limit is better. So that's the summary of, the way you would look at these. So let me put one of these alternating series that we just covered. I had this one actually on the exam a few years back. Clearly, since I'm writing it here, it's not going to be on the next test, but it says sine x over x squared. Let's go from 1 to infinity. Now you're looking at this thing, and you're wondering if this is this alternating? Well, first of all, what does it look like? Eventually.
Well, I'd say if it's square at the bottom, like P series there, it's right again. It's affecting. So it's n,
There's no 1 over x squared.
Yeah, but you have sine x. So it's going to be sine 1, sine 2, sine 3, sine of 4, sine of 5, sine of 6, sine of 7. What happened? Of course it oscillates. Very good. Of course it oscillates. Let me draw. Yeah, so this is pi, right? So number 3 should be here, which gives you this as a sequence. That's 1.5, so this is 1, this is 2, 1, 2, 3, 4, 5. This is terrible. No, hold on, this is pi. What am I doing? I hope no one is watching the stream, but it's going to stay recorded. This is where pi is for sine. This is where 2 pi is. So this means that numbers 1, 2, and 3. So 3 is very close. So here is 1, here is 2. So 1, 2, 3, and 4, 5, and 6, right? So what do we know? We see that sine of 1 is here, sine of 2, sine of 3, sine of 4, sine of 5, sine of 6, sine of 7, sine of 8, sine of 9, sine of 10, sine of 11, sine of 12. All right? We see it alternates. So it's alternating series.
So can you just assume any trig function since they all oscillate?
There are no any, it's just sine and cosine.
Yeah.
The other ones are not right tangent. Yeah. So this is alternating series. Now this problem, when you become trained in this section, this problem is exactly this problem here. I didn't use -1 to the n anywhere. I don't care in which way it oscillates. Does it oscillate as sine and pi? Does it oscillate as cosine and pi? Right? It doesn't matter. It is going to oscillate if there is a sine, if there is a cosine. So now you can solve this problem by simply repeating these steps. Because whether it is this thing, or the cosine term, or the sine term, it is alternating. Stage 1, you are testing the sequence, and our problem has 1 over n squared as well, so it's the same thing. Except this is now sine and the identical solution to the problem. If this was cosine and pi, it would be exactly this. Maybe just cosine of n would be, again, 3 terms and then alternate and then alternate. So there are ways. So it is absolutely the same problem as the one. So I'm just going to write.
Isn't that true?
What happened?
When you figure out that it's alternating series, the top doesn't matter at all.
No, that's not true, and we'll see why. Because right now we only had 1 over n squared. But what happens if you have k over k plus 1? Then you have something on top. So that's the next problem. Mm-hmm. So try this one on your own. -1 to the n times n over n plus 1. Go. Let's see what happens here. Yes.
So the sine one, that person wouldn't, but he's here in the wall. You see, it's here.
Yeah. How would you get the limit? Well, I thought it was yeah, so it's just part of yeah.
But it is
The exponents and values even during the same
It's one over one.
power.
Yeah, it was
Yeah.
one and number one.
Well, because like say if it was so if it was 2n over n plus 1, it'd be you plug in numbers.
Plug in two for n.
Anything's going on.
Yeah, it's one hand. I was thinking. Yeah, it's one hand, three quarters, 4/5. So they do it again.
All right, troops, let's take a look at the first order of business is to realize that an is equal to n over n plus 1, which is where the problem ends immediately. The limit of this is 1, which means that the conditions for convergence are not going to pass. You can also invoke divergence test if you want. It really doesn't matter. This thing is going to diverge immediately. So limit as n goes to infinity of n over n plus 1 is equal to 1, which is different than 0, which immediately implies divergence, and we are done with the problem. Now, many of you might be disappointed that we hadn't, we didn't have this elaborate thing to write and compute, but that is what it takes to solve some of these very quickly, very quickly. So you get to ignore this -1 to the n. Obviously, that was the one that tells you that once you figure out that the problem is convergent, which is what I call on convergent path, you have to push one step further and figure out the conditional or absolute convergence. Yes?
Why is inverse equal to limit?
The limit from Calc 1. You take, if the functions grow at the same rate, you take the ratio of front coefficients, which is 1 over 1. That's the theorem from Calc 1, which was last semester. I thought you were leaving all of this to us. Let's take a look at another. Oh, by the way, I'm going to show briefly the textbook. So the paper that I gave you has this, there is this version from this textbook, and as you can see, they have a little bit different order. It is the order in which is taught in this textbook. I don't particularly like the order, other than the fact that these two are, first of all, there's no telescoping on the list, right? As you can see there. And the divergence is not the first one on top, because, that kind of intuitively tells you, check me first, right? The same thing for integration. Always check for basic U sub first. And if you did that on a test, example number 2, you wouldn't be spending a page and a half working it out correctly.
Everybody who did retreat so good, right?
I don't know. I know you did.
That's fantastic.
No, I'm serious. I know you did, but I'm not sure if everyone else, because that's the. I can't remember everything. I remember a few grades, and then guys, I I gotta, I have other things to think about. I can't memorize everything, but I distinctly remember that you did it right because that was one of the first tests that I graded in terms of that problem. And I facepalmed myself, and then I was just like, all right, fine. But the argument was good and it's correct. Yes, all right, fine. Who was this again? Oh yeah, keep moving. So, all right. I guess you're requiring another problem. Look at the beautiful, as you would say, plethora of problems you have in the textbook. So you just the whole class picks me up. Look at that. Pick something you don't like and do it. So let's pick something you don't like. What do you don't like? 23 I heard. 22 I heard. We just did this problem.
I know, 22.
This is example 2. We said the cosine n pi is the one that is negative 1 to the n. This is example 2 in the note. Which one? 23. 23? Because it looks busy?
Yeah.
It's k to the 10 over k to the 11. So? Conditional convergence, just by looking at it. Now let's go through that argument. How do I know that this problem, I'm going to write it, without actually solving anything, skipping like all of the steps? How do I know it's conditional convergence just by looking at it? So let's go. Negative 1 to the k plus 1.
Yeah.
I will switch to tablet. I just need to write this. Oh, right, I'll switch to tablet right away. There we go. I have division of k to the 10 plus 2k to the 5 plus 1 divided by k times k to the 10 plus 1. And I'm telling you it's conditional convergence just by looking at it. Not even going to solve it. So, no. Could be k plus 1, k minus 1, k plus 10, it doesn't matter. So we don't worry about the alternating term, we just get to ignore that one. We are looking at AK term. AK term over here is what? Ultimately k to the 10 over k to the 11. The rest is irrelevant. So k to the 10 over k to the 11 cancels down to 1 over k. And what do we know for alternating 1 over k? That was the first problem we did today. It's alternating harmonic, it's conditional convergent. Why? Because it satisfies, it's decreasing, and its limit is 0, so it's convergent, but then 1 over k in a sum is divergent, so you have convergence followed by divergence means conditional convergence. So it's exactly this problem here that we did, except this is k and this is k. Yes?
Again, how you saw the feedback, but how did you know it needed to be
It's 1 over k. Because this problem over here, as I said, is k to the 10 over k to the 11, and just the rest of the garbage you throw away. Yes, you keep the leading terms, which is the highest exponents. True. So k to the 10 over k to the 11, when you distribute this k, you get k to the 11. So k to the 10 over k to the 11 is just 1 over k. And you have the alternating in front.
If the alternating function wasn't there.
You would do the comparison test to 1 over k,
Okay.
and it will still diverge by comparison to harmonic series 1 over k. It has to diverge. And this is, again, now I get to say, because you asked that question, which is awesome, I get to say one more time, this thing is convergent because the alternating term is there. If you take it away, it becomes divergent. You see, that's the reasoning, this little adjustment of throwing in alternating, it makes the problem convergent. It would converge to some number. You take that out, it will diverge. So convergence is conditional upon existence of the alternating term. For absolute convergence, any problem that's resolved and you get absolute convergence at the end, alternating term doesn't matter. Have it in or take it out, it will be convergent either way. So that's the difference between alternating and conditional convergent. I hope it makes sense, but then, as my good old high school teacher would say, If it doesn't make sense, it's not supposed to, because we just learned this. You go home, you practice this and train for about an hour, 2 or 3, and then it will be clear. And if it's still not clear, then keep doing it until it is clear. Such a motivation, right? I went to high school, so yeah. Yeah, I went to high school too. I have credentials to teach. I went to high school. Yes.
Can you just write the answer on the?
Yes, I am. I am going to. So ultimately, this is AK is 1 over K. I can also say compare to. And what do we know for it? So you are starting with our main series. You are checking decreasing, yes, and you are saying limit equals 0, yes. That means it's convergent. And then we have that summation 1 over K is divergent, which means conditional convergence. Done. Yay. Shall we do another one?
Yeah.
Yeah, why not? And then we're going to take a break. And when we come back, chapter 9, 9.1 power series. So one more example. Let's take something that I found a very good example. Good luck. Over there we go. Have fun.
Keep your hands involved, remember? This is walls sitting at the bottom. See what is your,
Well, I guess we have to know the other thing faster than
yes, the bottom.
the follow. Yeah, you're right.
All right, discuss, work with each other, enjoy mathematics. Is all good? Try to figure it out.
Yes, the key is this.
I know.
To help out.
And you do have to do like notes version or
No,
yeah. Because factorial,
one.
no, factorial is only just
Yeah, but you
well, I'm talking about you know, the first part.
oh, okay.
Conditions.
No, I plugged it. Duration, yeah, and then I plugged in like I plugged in a becomes 1/8 and then I got 1/. Well, no, the reason why I'm doing it this way is because of the K factorial. That's kind of like the idea I got. Because of the K factorial, you have to write it out this way, but you follow the rules of this. I don't know. We tried.
Well, no, because you now convert it mathematically. And then you just now absolute converge.
Yeah. But you get 1 plus 1. So you're saying, like, right now, let's take
Okay. Does anyone have a final verdict on what is the answer for this?
I think it's actually, I'm not sure if it's, I know it's convergence.
So you know it's on a convergent path. Now can we zoom in whether it's absolute or conditional?
I try.
I think it's up. I think it's up.
This is the wrong way to do it, right? Trying to set it up like the ratio. You have
But that's it. All right, guys, let's talk about this problem. Now, I want to do this problem in detail. All right, let's take a look. So we are starting from the original problem, and we have two branches, right? The branch can either go into convergence or divergence. We have to take a look at our AK term, and AK term is k factorial divided by k to the k. Now, the k, so AK term, we take a look if it is decreasing, and if the limit of the AK is 0. Now, as you can see, that are both trickier now than before. Well, actually not the limit, if you know the theorem, it's done immediately. But the decreasing part is. So let's talk about this. So first of all, this one, the limit one, says that we have to find the limit of k factorial divided by k to the k as k goes to infinity. Now, can anyone tell me what is the answer for this? Yes?
I know the k on the bottom goes a lot faster.
Very good. We look at the growth rate of functions. The function in the denominator grows much faster than the function in the numerator, which means slow growth over the large growth is equal to 0. So we have that condition fulfilled of the limit. Now we also have to check the condition on decreasing, right? Now, since this has a factorial, we actually have to check the inequality. In many cases, when you don't have a factorial or something crazy happening, you can take the derivative, right? And if you're getting negative numbers, right, if the derivative is negative, the function is decreasing. Hopefully we remember the first derivative test. I'm just saying. And if you take the derivative of the equivalent analog continuous function, then if the derivative is negative, it decreases. If the derivative is positive, it increases, which would fail the test. So the decreasing part, we are going to check, because for decreasing part, the next term has to be smaller. So the current term is k factorial over k to the k. The next term is k plus 1 factorial divided by k plus 1 raised to the k plus 1. Which means that if we want the decreasing, it has to be this way. And I have to put the question mark because I have to do this proof. But in order for me to prove that it's decreasing, now if this holds together with the limit, which already holds, then we are on the convergent path, and we just need to check summation of AK itself to figure out convergence, conditional or absolute. So we do the algebra here. Obviously, we are going to cross multiply. So I have k factorial times k plus 1. That's k1 plus. K plus 1, there we go. K plus 1. That should be larger, equal, and asking that still, as k to the k times k plus 1 factorial. Now I'm going to peel off the plus 1 where I can. So I have k factorial. K plus 1 I can't break, but I can do it to the k, and then I can put k plus 1 extra term, because this would be to the 1, and when I add them together, I get k plus 1. I'm still asking myself, so question mark, if that's true. On the other side, I have k to the k, and then I have k factorial times k plus 1, because we said last time we looked at it, if you peel off one of those terms, k plus 1, then the next term below is the one that takes the factorial, and so on. So now look what you know. You know that these are all non-zero terms. K factorial is a non-zero term. 0 factorial is 1. 1 factorial is 1. 2 factorial is 2. 3 factorial is 6. So k's are non-zero. K factorials are non-zero terms, which means I can divide both sides by them, and no harm done. Also, k plus 1 is a non-zero term. Even if k starts at 0, 0 plus 1 is 1, so it's a non-zero term, so I can divide by that stuff. The only question is if k plus 1 to the k is larger to k to the k, and the common sense would say, of course it is, right? Larger base raised to the same exponent must be larger number. So we are left with k plus 1 to the k is larger than k to the k, which is condition holds. So I will write words, since both the conditions hold, we have convergence. But we can still do better. We can still figure out whether it's absolute or conditional. Yes?
Could you just plug in numbers for k instead of doing all that?
I'm going to say no. And the reason is because if you remember when we did growth rate of functions, it took some time for some very fast growing functions to actually catch up and start winning. What happens if you use sufficiently small number? What happens if the function is so crazy that the actual observed decrease or increase would happen after 10,000th term, which could be possible. So doing the proof in general terms, where k is k, you can plug any number and it holds at the end, right? So my answer to you is, can you do it? The answer is yes, but you will get at some point so unlucky that something that could pass as a true statement is actually false. Because you are deceived, because you didn't do the proof. What you did is the example. The proof is all-encompassing. It means all cases, no exceptions. Where individual case, if you just take an individual case and look at it, right? Remember what is the glass and the water, and you just go to the ocean and you just scoop a cup and you say, well, no whales,
Yeah.
right? A small sample. Even if you calculated and checked it for 100,000 numbers, it's still a small sample because k goes to infinity.
Mm-hmm.
There's no way you can check.
So once the function, if it's always decreasing, will it always be decreasing? If it's decreasing in the beginning, it'll be decreasing whenever.
That's true.
So if I
That's
just
true.
pick 1, 2, and 3, then it's decreasing.
But then my argument was what happens if you don't see that until the 10,000 term?
It's decreasing.
Mm-hmm. And the 10,000, because the function can be very badly behaved for first 10,000 terms. And then after the 10,000 term, it starts decreasing forever.
Yeah.
And you checked only 1, 2, and 3.
Yeah.
If you look chaotic, it will look like it's not doing what it's supposed to do, and you say divergent. But then, it actually, after 10,000 term, it just goes and decreases. Because remember, whatever is badly behaved in the beginning, badly behaved, right? And then at some point after 10,000 term, it starts nicely decreasing like that. All of this bad behavior here, you can cut off. Here are the scissors. You cut that off, and you add manually those 10,000 terms. They're going to converge. And because the end of the tail goes like this, right? But let's say you check the first 3 terms and they were increasing, and you immediately concluded divergence because, right? You check the first 3 terms. I'm not saying that that's something that you shouldn't do because you're going to get the problem wrong. It's irrelevant about the problem, and no one cares about Calc 2 actually. When you start working and using these things, actually, it's very dangerous because, you know, the story of Sony exploding batteries and things like that, right?
Okay.
You don't want to be an engineer who makes those kind of things and those kind of mistakes. So it's a thorough check. You have to be careful about these claims. So the proof is the proof, and as Nike would say, just do it. All right, guys, going back to the problem. So that was the problem. We extracted AK from the problem, and we tested for decreasing, and we tested for the limit because we want to know that those 2 conditions pass. Once those 2 conditions passed, we claim convergence. Now we want to drill deeper and check if it is a conditional convergence or absolute convergence. So now you're supposed to solve the summation of AK, but your AK was k factorial divided by k to the k. Now I told you that when you have different types of functions mix, you use what? You use ratio test. So the ratio test was you have AK and you need to create AK plus 1, which is k plus 1 factorial divided by k plus 1 raised to the k plus 1. So limit as k goes to infinity, peel off immediately as you're plugging in, so k factorial k plus 1 divided by k plus 1 times k plus 1 to the k. Immediately times, flip the original one, k to the k divided by something, k factorial, there we go. We cancel k factorials, we cancel k plus 1s, and you are left with the limit k goes to infinity of k to the k divided by k plus 1 to the k in absolute values. And ultimately what you have is, now you do the limit, so you have the limit of k to the k, oh sorry, k over k plus 1, everything to the k, as k goes to infinity.
Can you go over how you pulled the k plus 1 out of the k factorial again? I know we did it before.
I will. And then we use from calculus 1 the limit theorem, which says that you can put everything to the k like this. Now what's the limit inside? Come on. What's the limit inside?
Zero.
1, thank you. Holy nightmare. It's 1. You have 1 divided by 1. Forget about the plus 1 over there. K divided by k. 1. Done. So, and 1 to the k is eventually 1. What do we know when the ratio test ends up being 1? It's inconclusive. We have to use something else. Inconclusive. Who picked this problem? So we have to figure out something else, because ratio test is inconclusive, and Let's try root test, see how that works. We have k factorial divided by k to the k. So this is going to be kth root of k factorial raised to the k over k to the k, which is kth root k factorial over k, everything to the k. Would something like this help? We don't know until we do it.
Wait, so when you got to the limit as k goes into k over k plus 1 all to the k, the fact that it's all to the k, is that how you can use the root test? Doesn't the whole function need to be raised to n or k or whatever it's going to be to be able to use the root test?
But I'm trying to fix it. As you can see, what I did is I created.
Like if I were to run into this on a problem, how would I know that I could use the root test?
Well, I see it to the k. That's why.
Oh, it doesn't matter where it is?
Well, I made one over here, right?
Yeah.
I made one because I didn't have one. I just want to see if it's going to work. So now they cancel, and I need to find this limit. All right. So the limits involving k factorial are not too fun in this respect. So, So we know that the k factorial grows much faster than the linear k on the bottom, but the problem is that we are taking the kth root of the k factorial. All right, so what are we gonna? Anyone has the idea of what we're going to do now with the k factorial raised because the ratio? Let me just check one more time ratio test to see if everything was done properly. So we have k factorial, k plus 1 is peeled off. We have k over here. So okay, and then we have a k to the k. These guys cancel. We have all of this raised to the k. It is divided by, and then when you multiply, you change division into multiplication, you have to flip it, right? The second fraction. So that's why it's k to the k over k factorial. This is supposed to be a division sign, but because it's multiplication, this flips. This one? The bottom is k plus 1 raised to the k plus 1. Because we are increasing every k by 1. Oh, the Wolfram test. There we go. Wolfram Mathematica test. Yeah, that one always works out, right? It's the ultimate test. So, see, no one will be able to solve it, but. All right, so this appears that it's all correct, and we pick this out, and it's 1 to the k, and the test is inconclusive. The root test, I don't want to do anything illegal over here, so I have to be careful. K, and then raise that to the k, and the kth root, so that doesn't work, so we're going to scrap that. Which means that we should be comparing this to something, but we can't, because it has a factorial. It's very interesting. I'll have to meditate on this one and then bring it. K plus 1, K plus 1, K plus 1 to the K, and then K to the K, and then K factorial, and they cancel, and we get this. Take the K. Raise to the K to the K. K plus 1, that's the limit of that is 1, and then 1 to the K, which is 1. Oh, wait! Yeah, 1 to the K. Yeah, I'll meditate on this one and I'll bring it back next class, so we'll figure it out. All right, so I'll take a look, but at least we know it's on a convergent path. Now we just need to figure out whether it's convergent or divergent so that we can claim either absolute convergence or conditional convergence. So in this case, we know it's on a convergent path. That's the conditions that we did for the sequence, and now we are supposed to just test the series. And if this series converges, we have the absolute convergence, and if this series diverges, we will have the conditional convergence. So I'll have to take a look and carefully solve this one. So I'll bring you next class because we are done in 2 minutes. So let's talk quickly about the project, and I need to upload that one more thing for the project. I'll stop the stream because we are done.